All right, coming up in a minute here, we have Kim Roberts with Sienna talking about 100 gig transport. Before we get to that, I'm going to announce our first survey winner from Monday. Is Linda Flores in the room? Linda. Come on, first winner. Not here. All right, going once. You get here? All right, okay, all right. You can actually pick up your the prize at the registration desk. Thank you very much, Linda. And everyone, please do fill out the surveys. There's actual prizes, and we use that information. I'm not going to stop badgering you. Coming up next, we have Kim Roberts with Sienna, talking 100 gig transport.
Good afternoon. I'd like to make this an interactive session if we can, given the size of the room. So if you have questions, find a microphone, and through the session, we'll try and recognize questions and incorporate, subject to the clock, what would work. If they're separate, you're not hearing anything there? Is that working better? Yes. If we can, despite the size of the room, make this an interactive session, I encourage you to use the microphones to ask questions through the session, and then try and leave some more time at the end for more specific questions. I'm going to talk about optical fiber communications, sending your bits from one place to another place. Specifically, I'm going to talk about single mode fiber, the stuff with the yellow jackets. I'm not going to talk about orange multimode. I'm not going to talk about new exotic research fibers, but good old single mode fiber. I'm going to try and provide an introduction while still providing interesting things for someone who's an expert in the area. There's a reference there for Chalk Talks if you want more introductory information. These are little short videos. Optical signals can be wavelength division multiplexed. We can combine the signals of different colors, different wavelengths. As shown here, you can have one signal and combine it with other signals that will propagate substantially independently down the same fiber. Shown here is 4 signals. Those 4 signals are formed as what's called a superchannel, so they can propagate together to the far end. And it's surrounded by lots of other WDM channels. And add-drop multiplexers and all the other aspects of the optical line can separate these and switch these. I'm not going to talk about any of that other than this introduction to say, this is the environment, and I'm going to talk about one signal. How do you get one signal to transport the information you want from one building to another building? The range of frequencies shown here is the C-band of the optical amplifier. I get the sense that this is booming. I'm hearing a lot of echo of myself. So within this C-band, you can carry 50 or 100 or up to 130 signals fitting in that 5 terahertz of optical spectrum. So what matters? What do you want from your optical modems? You want reach. You want your optical signal to go from this site to that site and be able to stay optical and not have to put a regenerator in between. Just like you don't want a regenerator in your ladder. Spectral efficiency matters. If we have continued exponential growth, that many of you are seeing 30, 50% per year growth, by 2020, we'll need to install 1,000 terabits of new end-to-end traffic in that 1 year. The optical spectrum is going to be squeezed. squeezed for sending more bits per second within that hertz of spectrum. In many applications, latency matters. Always cost matters. Heat matters, because from heat becomes not just air conditioning and electricity, but size and cooling and all the other aspects that flow from heat. However, there's physical barriers. There's physical barriers in the fiber that you have to overcome to send your information from here to there. I'll introduce a little bit what are some of these physical barriers before I describe how we overcome them. Single-mode fibers have chromatic dispersion. What is chromatic dispersion? If you look at a prism or a diamond, you're familiar with, you shine white light into it, you get a rainbow coming out of different angles, different colors. This is chromatic dispersion. The glass in the fiber has much smaller values of chromatic dispersion, but you got many kilometers of that glass. So the graph on the left shows as a function of wavelength. On the lower graph, the relative group delay, which is the familiar microwave measure, or in the upper graph, the optical measure, which is dispersion, in units of picoseconds of delay per nanometer of wavelength change per kilometer of fiber. So in the region of 1550, typical fibers have about 15 picoseconds per nanometer per kilometer of chromatic dispersion. This chromatic dispersion takes your pulse, as shown on the left with an eye diagram of a 10 gig signal, and smears it out. And so you get the signal on the right after dispersion. Where are the ones? Where's the zeros? Where do you do the sampling? Where do you recover clock? It's all smeared. Looking at the same thing in the language of signal processing, here's an impulse response. The top impulse response is from a single one surrounded by zeros with a raised cosine spectrum. You propagate that through 300 kilometers, you get the middle graph. You propagate that through 3,000 kilometers, this single one is overlapping with 150 of its friends. The traditional solution to chromatic dispersion was put in more fiber. Use dispersion compensation modules, like pictured here, that are coils of fiber, 1 to 20 kilometers of special fiber, which have the opposite sign of dispersion. They add delay, they cost money, and specialized engineering, and when you want to change what you're routing, you often have to send a guy with a truck out to change these again. Starting in 2005, I've made these obsolete. Another kind of dispersion is Polarization Mode Dispersion, PMD. Your fiber is not completely circular, and the cable is not completely straight. That means that any particular millisecond, you have a fast mode and a slow mode. And so your signal gets coupled into these and smeared out because some of the energy arrives before the other energy, as shown in the icons here. There's a lot of PMD in the fibers. At this workshop in 2007, the phrase was used, PMD is like dirty underwear. Everybody has it, but nobody talks about it. You don't want to admit that you have PMD in your cables. This is a pie chart that was anonymously assembled from different British cables. 0.05, 0.1 picoseconds per square root kilometer are fibers that are meeting modern specifications. You see all the rest, 0.2, 0.5, 1, are fibers that have a lot of PMD. And then you get huge amounts of PMD. We'll see in a few slides later how 10 gig propagates on this, and then how 100 gig will propagate. Noise is always a challenge to communications. I'll be using in this presentation the units OSNR, the Optical Signal-to-Noise Ratio, This is the power in the optical signal divided by the power measured in 1/10 of a nanometer of the noise spectrum, expressed in dBs. The thing to remember for amplifiers and the line system, delivering a large number is good. That means you're delivering small amounts of noise. Conversely, for a receiver, tolerating a lot of noise is good. So you want to have a small value of tolerated OSNR. And the gap between those two is how much margin is left. What is the noise in an optical transmission signal? Well, obviously it's optical noise. Amplifiers are used to overcome the fiber losses. The gain in the amplifiers inherently add photons, stray random photons. It's optical noise. Shown here, the eye on the left is coupled into the fiber, and after amplification, you get the same eye on the right with added Gaussian optical noise. Well, why don't I just raise my signal power so I have a better signal-to-noise ratio? Glass is a nonlinear medium. You raise the power, you get stronger nonlinearities. And these are the primary nonlinearity is the Kerr effect. Shows up as self-phase modulation and cross-phase modulation. Very interesting, but very complicated. I won't be spending any time on it in this session, other than it limits the power that we can use on your fibers. A way to reduce noise is to have lower fiber attenuation. You already operate in what's called here the third window, where the fiber loss is the lowest. But you can use lower loss fiber. The blue curve is showing a typical fiber of 0.19 dB per kilometer. This example from Sumitomo is 0.149 dB per kilometer of loss. Lower loss translates to less noise, meaning you can send more data or you can send it farther. Another way to reduce noise is to optimize the amplifier spacing. The optimum spacing is about 14 dB of loss. However, 14 dBs might be a very inconvenient location, like the middle of this swamp. Another way to reduce noise is to add RAMAN amplification. RAMAN is a nonlinearity that can be used in the fiber, so you get a small amount of gain occurring inside your cable. You create this by putting high-powered lasers, high-powered pumps, to pump your fiber and make it amplify. You can get 3 to 4.5 dB of OSNR improvement with commercial products doing this. However, there's a danger coming from that high pump power, danger to humans and also danger to your fiber. If you've seen a patch panel like on the left, it can contain connectors you don't know about. Connectors that are looking like the right microphotograph of a dirty connector. You get a dirty connector and you put RAMAN pump powers through it, it explodes. It vaporizes the connector. In order to ensure human safety and safety of your fiber, what we've done is built in an OTDR into the RAMAN card. An OTDR is an optical time domain reflectometer. This is a box that's carried in the truck of your fiber tech. And traditionally, they disconnect the fiber from the equipment, they send a pulse from the OTDR down the fiber, measure reflections coming back, and they can see if there's any problems in that fiber. But you need the guy, the truck, the box, and it disconnects your equipment. With this feature, it's built into the equipment, and it can run in service, and more importantly, the RAMAN doesn't turn on until it passes the OTDR test. So it's connected and it's not going to melt anything. A single mode fiber carries 2 polarizations. If you remember from way back when, propagation of a plane wave can be broken down into 2 orthogonal polarizations. linear or circular. If it's circular, it could be left-hand circular, right-hand circular, or if you consider it as linear, it can be this and the perpendicular one. So I can modulate a signal onto both polarizations. Put one signal on this polarization, put a different signal on the other polarization, and send twice as much information. Again, if you think from way back when, remember your complex numbers. You have real and imaginary. Or in the language of microwaves, you have in phase and quadrature, I and Q. For many generations, we've used what's effectively Morse code. We've turned the light on and off. We send 0, which is the central point on this complex plane, and we send 1, which is the circle. We don't care where you are in the circle, it's just you have power or you don't have power. And we've, each generation, been turning the light on and off faster and faster and faster. But for maybe 50 years, radio systems have used more complicated modulations, such as QPSK, quadrature phase shift keying, where you never send 0, where the axes cross. You're always sending power, but the information is encoded in a phase. Shown here, you can encode 2 bits in each of these 4 constellation points. And so you communicate 2 bits in this polarization, 2 bits in the other polarization. If you send this 10 billion times a second, you're sending 40 gig. If you send this 25 billion times per second, you're sending 100 gig. So we need to be able to send these kinds of constellations. CMOS has advanced to where the digital signal processing can be made fast enough that we can do this for 100 gigabit signals. Your data comes in from the left. We apply digital signal processing, encoding, filtering. The output goes to 4 digital analog converters, which drives the modulator, which creates the signal. Here's a view of the hardware with the lid taken off, so you can see the CMOS chip. That snaps into the modulator. When you have a digital analog converter, I can do all sorts of things. I can shape the spectrum. Shaping the spectrum is important because if you do the traditional on-off keying like this, where you have 1s and 0s, you look at the time, you get a conventional eye diagram as a function of time. But you look as a function of frequency, curves aren't showing very clearly from this angle, but you can see the sync functions. You have all these side lobes spilling out, interfering with neighboring signals. If I use a raised cosine spectrum as a function of the parameter alpha, I can change I'm hoping you can see it with a better angle there. I can change the spectrum. So I can create down to alpha of 0.14, very flat-topped, very steep-sided signals that are very nice to stack together side by side with other signals. I can get them very close together and they won't interfere with each other. I can do this because I have a digital analog converter in the transmitter. Another application of that DAC came up Christmas time. One of you had a network where you had a German manufacturer of the line and you wanted to run my signals over it. Unfortunately, that manufacturer looked at my signals and said, those aren't signals, they're noise, and wouldn't turn on, wouldn't let the switches pass the information. You asked that manufacturer to fix their software, they refused to fix their software. And so you told us about the problem, and we created what we call the Prussian helmet signal, which is the red curve. Instead of the optimum root raised cosine, which is the blue curve, by sending you the firmware a week later, you were then in service with the red spectrum, which was close enough to a signal that that manufacturer recognized, oh, there's a signal, I will turn on my switches now and let that pass. You can do this because the DACs are there, and the DACs are controlled by the firmware that controls the signal processing, shapes the spectrum. In this case, it's not optimum. You lost about a dB of performance, but it overcame the software problem with optical methods. The receiver, coming from right to left, we have 4 signals coming from the coherent receiver that I won't describe in detail today, coming into analog to digital conversion, digital filtering, digital signal processing, decoding the modulation, forward error correction, and then error-free your signal coming out the left. This is the chip that does the heavy lifting on the receive signal processing. It does 70 trillion integer operations per second. Implemented in 32 nanometer CMOS, contains 150 million gates, and contains almost 4 kilometers of copper wire. It's about 18 millimeters on a side. So we put those pieces together, and you have your 100 gig link. Transmit signal processing, driving a transmit modulator, going over your optical line, coming to a coherent receiver, and the receive signal processing. There's a picture of the card, plugs into a standard shelf. The card's about the size of a textbook, or a small laptop. So this card does transmit and receive 100 gigabits or 200 gigabits. So how well does this overcome the physical challenges? Well, let's look at chromatic dispersion, which smeared out the eye. A 10 gig system tolerates about 1,000 picoseconds per nanometer of dispersion away from the optimum value. The Flex 3 version of the 100 gig card tolerates 300,000 picoseconds per nanometer. More specifically, we look at them as a function of the amount of dispersion, what is the noise penalty experienced? You see that up to 270,000 picoseconds per nanometer, almost at the very far right, there's a very small noise penalty, and then the penalty starts to take off. Look at the middle, 150,000. That's 10,000 kilometers of ordinary fiber. So you don't need to worry about dispersion anymore. What about PMD? Well, here's a very boring graph. Look at the red line. It's effectively 0 penalty within their measurement accuracy, which is about the thickness of those dots, out to 400 picoseconds of PMD. To compare that with 10 gig, 10 gig tolerates for a 2 dB penalty 15 picoseconds of mean PMD, of average PMD. WaveLogic 3 tolerates 10 times as much. So you don't need to worry about PMD. You have old fibers that you can't use on 10 gig because of too much PMD. Use them for 100 gig. Use them for 200 gig. Specifically on the pie chart that we had a few minutes ago, you see that even for 0.5 or 1 picosecond per root kilometer, where the reach of 10 gig is getting smaller and smaller, the blue numbers, the orange numbers are still showing 3,500 kilometers of reach. Only when you get up to 3 picoseconds per nanometer, 3 picoseconds per root kilometer, do you start to get any reduction in the reach. No one's been brave enough to ask questions in the middle yet. I'll keep going. Spectral efficiency. 10 gig allows, for example, a 10 gig channel at a 50 gigahertz spacing, which gives you 0.2 bits per second per hertz when you divide those two. Flex 3 version of Ciena's card will offer you, say you wanted to configure it at 400 gig in 80 gigahertz. That's 5 bits per second per hertz. You still want more spectral efficiency, but this is a factor of 25 improvement. There's never enough. Let's look at the example of QPSK, quadrature phase shift keying. Using this, we deliver 100 gigabits per second in, for example, 50 gigahertz of optical spectrum, using these 4 points of the constellation. You see, the points are not really points. They're fuzzy clouds because of the added noise. And the distance separating these points determines how much noise tolerance I have. The bigger the separation, the less likely to make mistakes in deciding is it in this point or that point, and too many mistakes overwhelms the forward error correction. This graph showing the performance of a typical line with QPSK, where the horizontal axis is kilometers. The vertical axis is the OSNR, the Optical Signal-to-Noise Ratio. The blue dots at the top are showing the measured received OSNR on a particular line in our labs. The red circles above that are simulations, what would happen if you added RAMAN on every span. Simulations let me carry on out beyond where I didn't have enough amplifiers to go to, towards 5,000 kilometers. The curves on the bottom are the measured and then the simulated performance of the receiver. How much noise can it tolerate? And the vertical distance between that and the noise provided at the line is how much margin you have, how many dBs of margin you need. And you see here with QPSK, you have plenty of margin at, say, 3,500 kilometers of reach, and longer if you include RAMAN amplification. Where these lines cross is where the system won't work, where your margin's going negative. You don't always need 3,500 kilometers. Maybe you only want to go 500 kilometers. But the distance you're going is one way of describing the noise tolerance. You don't have to use the tolerance to nonlinearity and the tolerance to noise for long reach. You can use it for other degradations in your network to handle high span losses, ROADMs, which are reconfigurable optical add-drop multiplexers, patch panels, nonlinear interference. What if you do want reach? If you want really long reach, you want to cross the Pacific. Well, instead of using 4 points for QPSK, we use 2 points for BPSK, as shown here with the 2 points on each polarization. Because we're only encoding half as much information, we send 2 carriers as a superchannel, as shown in the spectrum in the bottom part of the graph. And the picture on the right is a picture of our lab showing an emulator of an undersea cable, where we have amplifiers and fiber to emulate trans-Pacific cables. What reach do you get with BPSK? Sorry, I'm out of sequence here. Here's 200 gig. We'll get to BPSK in a minute. If you want to send 200 gig, you can use the Constellation 16 QAM. You see, with RAMAN, the red points, you have plenty of margin after 1,200 kilometers of sending 200 gig on each wavelength. And now we have the BPSK. The green points are QPSK measured on undersea. Undersea, you go farther because you have optimum amplifier spacings, you have low-loss fiber, you have low-loss amplifiers, low-noise amplifiers. You go farther on an undersea system than on most terrestrial systems. The red points are BPSK, and where that intercepts the horizontal black line is showing adequate margin for an undersea system on, say, 13,000 kilometers. Or with the new 8-dimensional modulation, this product will go 16,000 kilometers, anywhere you wanted to go around the Pacific. And finally, to show the flexibility of the WaveLogic 3, my son was given a couple of WaveLogic 3 cards, and he wrote some firmware, not for use in your network, but just as a demonstration of what kind of things you can do with the signal processing. So these are production WaveLogic 3 cards. What we're going to see is the signals that were captured at 35 billion symbols per second. We capture a small fraction of them and display them on the screen. We're running a 10 gig Ethernet test set, daisy chain through the system, and it's error-free through the entire demo, including the transitions we're going to have between different kinds of constellations. After FEC, the Ethernet traffic was still error-free. So we start off with BPSK. Left-hand side is the X polarization, the right-hand side is the Y polarization. We're putting BPSK on both. And I'll start the movie. I think I'll start the movie. There we go. We have BPSK, and we're grabbing it. And you see now it's slowly evolved to QPSK. Still error-free while it evolved. And then it's gone to 16 QAM on each polarization. And then because he didn't know any better, he went to 64 QAM. Eight PSK. Still error-free all through this. 4 PSK and 0. And he's purposely made these transitions slow so we can see how they're varying and how it's error-free while it's varying. 3 PSK. 8 QAM. One of the versions of 8 QAM. And then 35 billion. There's just 35 billion happy faces per second, still error-free. The 10 gig Ethernet's daisy chained. And then before he was born, there was a game called Pac-Man. I asked, well, what about the ghosts? But he couldn't get the ghost error-free, so it had to only be the Pac-Man. And if you visit our lab, we run this demo, and it runs around in a loop, and it's going back to BPSK, and it'll keep running around there in the background as eye candy when you're talking to us in the lab. And there you can see the test set and see it is indeed error-free. Thank you very much. There's lots of time for questions, so I'm hoping you have questions to take in directions of your interest. Is the microphone? Unless you're really loud, you'll need to use the mic. I don't have control of the slides to be able to jump around to pictures that you want to refer to.
Okay, so you went to 64 QAM because you said he didn't...
Sorry, can I ask you to identify yourself, please?
Oh, I'm in trouble now, aren't I? Matt Petak, Yahoo, sorry. You said he went to 64 QAM because he didn't know any better. You're running this at 10 gigs, so you got away with that error-free. What would have happened
the
if you...
10 gigs daisy chained. The 10 gig was just
Okay.
a standard test set, and it was daisy chained through the system.
Could you have done 100 gig at 64 QAM?
This is experimental to show in the lab. I'm not suggesting that you want to run this in your network.
Gotcha. So this is one of those, maybe it'll work, maybe it won't. Hey, it'll make for a great movie, but no way in hell would we suggest you actually try to run real data through this.
On WaveLogic 3?
What?
No.
Okay, gotcha.
On WaveLogic 4? Well, talk to us.
Randy,
I wouldn't suggest Pac-Man in your network either. This is just done to see what can you do with the existing hardware.
Randy Manning. This might be a little off topic, but any application that runs on your cards, like latency tests or anything like that, that we could pull off your cards?
A slide that I pulled in the interest of time was describing latency, but it's in the proceedings there, where the effect can be adjusted on the appropriate version of software in the card. You can change the effect latency, so you determine what the latency is that you want. We don't have variable latency. The latency is fixed. You choose what the latency is. You give me more time, the effect can chew away and correct more errors. If you have plenty of noise margin, then you can set the latency smaller. The effect is what dominates the latency. The numbers are on the chart about halfway through the deck.
More questions?
Dan McGorian, Hopkins APL. I've never actually understood why RAMAN amplifiers are more expensive than EDFAs when actually they're simpler, and except the fact that they're sold in a lot smaller volume to a much more specialized market.
It's the power of the pumps.
Pump laser is intrinsically a lot more expensive.
An EDFA consists of
Yeah, I know what it is.
lasers, which I use 980 nanometer lasers, which energize the erbium, and the erbium are ions in about 50 meters of glass in a little coil. The rest is mechanics and monitoring and control. That's an EDFA. RAMAN, you have mechanics, monitoring, control. You don't have the coil of erbium because you're using your cable, but you have watts of pump power.
All of which
instead
ought to
of
make it
milliwatts of pump
simpler and less expensive.
So it all comes down to the cost of high-powered lasers.
Yeah, which comes down to volume, right?
Comes down to yield.
Yeah.
And so, yeah, RAMAN has all the safety issues that we think we've overcome, but also has cost. You use it when you want the performance. Cheapest amplification is C-band EDFA.
Hi, Spike Curtis, Metaswitch Networks. Are there physical limits to how high you can go with like bits per second per hertz, like Nyquist or things like that, or is it more or less unlimited if you get lower and lower noise amplifiers and things like that?
It's a function of the noise. Of course, it's a function of your implementation, but you're not worrying about my problems. You're asking, what's the theoretical limit? It's limited by noise. What's your signal-to-noise ratio? Shannon says, in linear propagation, if you have this signal-to-noise ratio, you can achieve that capacity in theory. And leaves it up to the student how to figure out how. And he says, you cannot go faster than that. So on practical systems with practical noise levels, it gets challenging to go more than 6 bits per second per hertz, maybe 7. I've shown measurements of products where you can go 5, and you can squeeze them a little closer together to get, say, 5.5. Next generation, you'll try for 6 or 7, but 10 is really hard given the kind of noise that you want to tolerate. Inside your building, in a lab with carefully tuned everything, well, heroic things can be done with 1024 QAM, but it's not practical in a real network with real noise. So that is the big challenge that's left. As you saw, all the other degradations, all the other linear degradations have been fixed with plenty of margin. You don't need to worry about them. You don't need to worry about dispersion or PMD. They're gone. Noise and its complement nonlinearity, that's the challenge that remains. That's why the emphasis on lowering the noise, so that we can use more complex modulations and send more bits. It's only possible with less noise. We can improve forward error correction, we can improve the signal processing, but that gives us 1/10 of a dB here and 2/10 of a dB there, and we're reaching diminishing returns. There's no more easy doubling for capacity, which means your spectral efficiency of how well you use your spectrum is not going to get much better than, say, 6 bits per second per hertz.
Last call. All right, thank you very much, Kim. Wonderful material. Thank you.